This chapter testbench examples. The UVM testbench, example 1. The UVM verification testbench example. This session is a real example of how design and verification happens in the real industry. We will go through the design specification and write a test plan with details how the design will be tested, develop a UVM test bench structure, and verify the design. This is a simple pattern detector written in a Verilog to identify a pattern in a stream of input values. On every clock, there is a new input to the design, and when it matches the pattern 1011, the output out will be set to 1. For this purpose, the design is implemented as a state machine which moves through different stages as it progresses through a pattern identification sequence. Test plan. The verification test plan will be developed in UVM and has the following block diagram. The sequence generates a random stream of input values that will be passed to the driver as a UVM sequence item. The driver receives the item and drives it to the duty through a virtual interface. The monitor captures values on the duty's input and output pin, creates a packet, and sends it to the scoreboard. The scoreboard is primarily responsible for checking the functional correctness of the design based on the input and output values received from the monitor. The input stream of the values has to be random for maximum efficiency. It should be able to catch the following scenarios: 011 and 011, 011, 010, 1010, 1110, 1110, 00100, 1011. Test bench and sequence item. This is a basic transaction object that will be used in the environment to initiate new transactions and capture transactions at the DUT interface. Sequence and driver. The driver is responsible for driving transactions to the DUT, or it is to get a transaction from the mailbox if it is available and drive it out the DUB interface. And monitor. The monitor has a virtual interface handler with which it can monitor the event happening in the interface. It sees the transactions and captures information into a packet and assigns it to the scoreboard using another mailbox. Scoreboard. The scoreboard is responsible for to check the functionality and should track input and try to match the pattern, ensure that the design have found the pattern as well. The scoreboard should flag an error if the design didn't find the pattern and ensure that out remains 0 if the design found the pattern. That out is set to the correct values. Agent in the environment. Creating an intermediate container called agent to hold driver, monitor, and sequencer. The environment is a container object simply to hold all verification components together. This environment can be reused later, and all component in it will be automatically connected and available for use. Test. Since we want to be able to truly use the same verification environment to detect design with patterns other than 10, 0.11, it has to be developed with enough flexibility to easier change the pattern. For this region, we have choose to represent the pattern as an n value where n is defined by the macro length as 4. Also, base test sets up the environment, config underscore db and other parameters for test, so the derived test simply have to provide a new pattern if required along with the total number of data items to be sent to the DUT as input string. Number of data items to DUT is a randomized value that is a part of a sequence and randomize the different values in the derived test. And interface. The interface allows the verification component to access DUT signals using a virtual interface handler. And testbench top, and design volume 1.0, 1.0. And when we simulate this design in our verification environment, we can see that there are many errors. The verification engineers debug the error to confirm that these are design bugs and are reported back to the designer. The design bugs his design to find the root cause of errors, assume that he has fixed all errors and release the second version of the design. Design 1.1. The designer assumed that if next input is 1, state should start from idle, but he forgot that he should stay in the same state since it already matched part of the pattern, which is the starting one. The verification engineer relearns the same test using the same verification environment on the second design, and found out that the number of errors have decreased but not zero yet. Another ticket is raised to the designer to debug and fix his design, which still seems to have many bugs. The designer realizes some of the errors and released another version. Design 1.2 fixed the bug found in 1.0, and the designer assumed that if the next input is 0, then the pattern failed to match and should restart. But he forgot the S101 followed by 0 actually match the part of the pattern, which is 10, and only 11 is remaining, so it should actually go back S10. And next S1, fix for bug found in version 1.1. The verification engineers run the same test on the same environment and see that although errors have reduced, it is not zero yet. Let's assume another ticket is raised to the designer who debugs again, finds out that he missed to take some scenario under consideration and fixes the design to release 1. Version 1.3. Design 1.3. The designer assumed the next state should always be idle since the pattern has matched, but he forgot that the input if if next input is 1, it is already start of another sequence and instead should go as 1. So rerun the same test on the design. We will see that the number of errors has come down, but not zero yet. Again, the design looks into the errors and fixes those errors and provide version 1.1.4. Design 1.4, version 1.4, Finally, all errors has been solved and the design is now bug-free for given seed. Now the test has to pass hundreds of seeds to ensure the design is bug-free. Ideally, the designer should run the test and resolve all bugs before making a design release, as this would reduce turnaround time significantly. So mention log are like that. Thank you. So now, next is Testbench Example 2. System Verilog-based Testbench was explored before to verify a simple design that sends incoming packets to two output ports based on address range. Let us build a similar testbench using UVM component so that you can compare it with the traditional System Verilog testbench. So, sequence item. A class called switch underscore item is defined to hold random input address and data. It also has variables to hold output address and data so that they can be compared easily in a scoreboard. The pros and cons of this method will be discussed later. Here, address underscore A and underscore data underscore A represented the output packet that comes from port A of the design, while address underscore B and data underscore B represent output packet that comes from port of the design. Since only one packet comes out of either port A or port B, use the same class object is okay. The class also has utility macros to help with common requirements like print, copy, and clone. This, in the example, this is the base transaction object that will be used in the environment to initiate a new transaction and capture transaction and DUT interface. Next is the UVM driver. The UVM driver extends from the UVM underscore driver and is parameterized to accept an object of a type switch item. It also receives a handle to a virtual interface that is used to toggle pins of the DUT. The driver uses standard method called get next time and item done to communicate with each sequencer. So UVM monitor. The UVM monitor is derived from the UVM monitor and has a virtual interface handle to listen to activity on the given interface. It tried to decode pin level activity into a protocol packet, which can be sent out the other test bench component. In this case, it tried to see if address and data pairs are available on the duty interface, capture them into a class object of type switch underscore item, and send out via an analysis port. Since it has to decode and capture any activity happening on the duty interface, it has to run for as long as the simulation is active, and since it is placed inside a forever loop. Note that every packet that is sent on each input port should be found on one of the output ports. The monitor will capture input port on every clock and capture both output ports on every clock and send a complete packet to scoreboard. This makes the monitor slightly complicated. We will see an alternative strategy later that shifted the complexity to scoreboard instead. UVM agent. The role of a UVM agent is to encapsulate the sequencer, driver, and monitor into a single container. The sequencer is responsible for acting on a given sequence and send the driver with data object. It's parameterized to accept object of a type switch underscore item and its SEQ item port is connected to drivers SEQ item export. So the next is the UVM scoreboard. The scoreboard receives the data object through its UVM analysis input port from the monitor. Since our monitor captures an entire transfer, both input and output data, implementation of scoreboard becomes really simple. Since we know from the design specification that addresses is less than a specified value should go to output port A, and those that are above should go to port B, the checker logic can be implemented on that basis. As soon as the scoreboard receives an item, its write method will be executed, which in turn runs the checker and predicts the result. The UVM environment. The UVM environment is responsible for instantiating and connecting all test benches components. Here, analysis port from the agent monitor is connected to the analysis implement port in scoreboard. This connection allows the scoreboard to receive a packet whenever the monitor pushes new data into analysis port. The UVM test. The test instantiated an environment such as a virtual interface handles two subcomponents to start a top-level sequence. In this simple example, we have chosen to also reset the DUT using a reset task, after which a sequence of a type gen underscore item underscore SEQ is started on the agent sequencer. Since the sequence consumes simulation time and all other test bench component has to run as long as the sequence is active, it is important to raise and drop an objection appropriately. And UVM sequence. The last but not the least, we have the main sequence that forms the stimulus and the major aspect of the test bench. The sequencer, when started on a sequencer, gets the body method executed, which ultimately randomized address data and send them to the driver. This is simulation log. The next is UVM verification example. The UVM verification test bench example. This is a real example of how sorry, I think it be okay. I think it's a some duplication or replicative of the previous sections. This section is a real example of how design and verification happens in the real industry. We'll go through the design specification and write a test plan, details of how the design will be executed, develop a UVM test bench structure, and verify the design. Design. This is a simple pattern detector written in a Verilog to identify a pattern in a stream of input values. On every clock, there is a new input to the design, and when it matches the pattern 1011, the output out will be set to 1. For this purpose, the design implemented as a state machine, which moved through the different stages as it progresses through pattern identification sequence. Test plan. The verification test plan will be developed in UVM and has to follow block diagram. The sequence generates a test random stream of input values that will be passed to the drivers as a given sequence item. The driver receives the item and drives it to the DUT through a virtual interface. The monitor captures values on the DUT and the input and the output pin, creates a packet and sends it to the scoreboard. The scoreboard is primarily responsible for checking the functional correctness of the design based on the input and the output values it received from the monitor. The input stream of the values has to be random for maximum efficiency. It should be able to catch the following scenarios: test bench, sequence item, sequence, and driver, and monitor, and scoreboard, and agent and environment, and test. Since we want to be able to reuse the same verification environment to detect the design with the patterns other than 1011, it has to be developed with enough flexibility to easily change the pattern. For this reason, we have to choose to represent a pattern as an n-bit value where n is defined by the macro length is 4. Also, the base test sets up the environment, config underscore db and other parameters for the test so that derived tests simply have to provide a new pattern if required along with the total number of the data items to be sent to the DUT as input stream. Number of data items to DUT is a randomized value that is a part of the sequence and randomized to different values in the derived test. So interface and test bench top and design 1.1 is when simulating the design in our verification environment, we can see there are many errors. The verification engineers debug the error to confirm that these are design bugs and are reported back to the designer. The design debugs in his design to find the root cause of errors, assume he has fixed all the errors and releases a second version of the design. Design 1.1, version 1.1. The verification engineer rerun the same test using the verification environment on the second design and find that the number of errors has decreased but not zero yet. Another ticket is raised to the designer to debug and fix his design, which still seems to have many bugs. The designer realized some of the errors and realized another version. Design version 1.2. And the verification engineer rerun the same test on the same verification engineer, sees that all the errors have reduced, but it is not zero yet. Let's assume another ticket is raised to the designer, who debugs again, find out that he missed to take some scenarios under consideration and fixes the design to release version 1.3. Design 1.3. Okay, we run same test on the design and we see the number of errors has come down, but not zero yet. Again, the design looks into errors and fixes those errors and provide version 1.4. Design 1.4. Finally, all errors has been solved and the design is now bug-free for the given seed. Now the test has passed hundreds of seeds to ensure the design is bug-free. Ideally, the designer should run the test and resolve all bugs before making a design release, and this would reduce turnaround time significantly. Thank you.